Hello everybody. In this video I'm going to talk about one important thing that is important for everyone who uses Matlab for solving differential equations to know. In the previous videos, starting from the first numerical solution video that we started using the ODE 45, we have been using only the function that's called ODE 45 to solve one differential equation, simultaneous equations. And we saw different examples on the tank that's emptying from the orifice and for the PFR. And it was working pretty nicely and fine, and we didn't have any problem. However, the point that I want to make in this video is that you need to know that this is not the only function that is available in MATLAB for solving differential equations numerically. To understand the point more, I would go just with a simple thing to go with the help of MATLAB to know some information about the ODE 45. And from the help, you would see there are a lot of information here about the syntax and about many things, but the important thing that I want to highlight now is this. This is solving the non-stiff differential equations. All these information below are either information that we have already discussed before, or some information about the syntax or mathematics that is not the point of this video. But you would see here that MATLAB suggests some other functions that are similar to the ODE 45. There is ODE 23. If you see here in the help of the ODE 23, it solves the non-stiff differential equations lower order method, and here medium order method. I do not I do not know what do they mean by medium order or the lower order method or low order method, and this might be something that you would find in the literature or in the MATLAB help and documentation if you're interested in. At the end of the day, we are just users, or at least I am just a user. I need to find a way to get my problem solved. If this works, I'm okay with this. But the common thing between these two functions is that it says they solve non-stiff differential equations. There are some other functions, there are a lot of functions here, but the point that I want to make is to notice that there are functions that have letters at the end. So like ODE 15S, ODE 23S, ODE 23T, and then TB, and then I. And it's important for the users to understand what is the difference between these. For instance, if you see the ODE 23S, you would see that it tells you that it solves stiff differential equation. And this is one important point that a user who solves differential equations using MATLAB must understand, that what is the difference between stiff differential equations and non-stiff. A stiff is kind of material property. It's like a piece of wood might be stiff. It's hard for you to bend or to break, and this is the stiffness. But when you do talk about the stiffness in differential equations, we mean that the function is not easy to integrate numerically. So for instance, if in the normal cases, when we do the integration, we start with the initial value, and we take increments, and from each increment we calculate the second, and from the second you calculate the third, and so on till you reach the end of the time span or the distance span, whatever the independent variable is. In the normal cases, there is no problem from going from one point to the other. In stiff differential equations, it might be difficult to go from one point to the other. You might get very big difference in the values. It might be like shooting up or shooting down. The function itself is not easy to track. So in this case, you need to go with closer points. You have to go from, instead of taking an increment of 1 second, for instance, you need to take half a second, quarter second, tenth of a second, so that you get reliable and accurate results. So in case of these functions, you use the ODE 23S, which deals more with the stiff equations, differential equations, more accurately. The stiffness of the function can be depending on the function itself or the equation itself. It is stiff by its nature, or it might be function of the parameters that you use to solve the function, like the initial values or the time span or the distance span. So we will see an example here of a function that was not stiff, and then at some point it became stiff. You'd see some other functions that end up with letter T, like ODE23T, and if you look at the T, it says it's moderately stiff. So it's not totally stiff, and it's not totally normal or regular function. It tells you it's moderately stiff ODEs, it's ordinary differential equations, and DAEs. DAEs means it's differential algebraic equations. So you have a system of equations, some of them are differential and some are algebraic. So in case you have a problem like this, you can use the DAEs. So T is kind of between the stiff and non-stiff functions. And it uses the trapezoidal rule here. It tells you that use trapezoidal rule. Something like this, it's ODE 15I, or let's see the TB first. It tells you that it solves stiff differential equations, not moderately stiff differential equations. Again, the differences between the ODE 23S and the ODE 23TB can be found from the documentation. I'm not here to talk about the differences in details. I'm just highlighting the available functions and what's the difference in equations that you can face. The I, it solves fully implicit differential equations. The equations that we solved before were explicit, meaning that you can put the differential term on one side, like dc by dz or dt by dz or whatever, and then the rest of the parameters on the other side of the equation. The implicit equations cannot be treated like this. With all mathematical manipulations that you can do, you will not be able to have the function as d by d term on a side and then the other parameters on the other side. So this is a case that requires an ODE 15I that can deal with. So I'm not going to go into any more details. Again, I'm just opening up the topic for those who are interested. Again, about the stiffness of the function and non-stiff, you will face a lot of things, especially for the coupled equations. If you have 2 or 3 equations solved simultaneously, you would very likely face a case like this, that you have stiffness in the solution or in the differential equations. I already faced the problem like this before. I was solving like 3 or 4 differential equations simultaneously before, and I found that the ODE 45 is not giving reliable results. So I had to shift to another ODE function that was able to give me a more accurate solution. And at the end of the day, again, I'm just a user. I find the proper function that will do the job for me, and I'll be happy with it. So the last thing that I'm gonna talk about in this video today is an example of the stiffness of the function. So if you remember this case that we discussed before of the tank, the open tank versus the closed tank, and they were draining from an orifice. So if you remember before, we put the end time was 520 seconds before, and this was the time that the tank wanted to reach the equilibrium. I'm just going with the closed tank. I'm not plotting the open tank to prevent any confusion. And when we run the file, we were able to see the profile of the height started from 13 and it went down, down, down till it reached the almost 5 point something, or almost 5.8 meters or something like this. If you change the end time and you did the integration, and of course you understand that at this point the tank has reached its final height, so it's not even after like 5-10 minutes more you'd find no change in the height, because I'm not changing anything in the parameters in the system. So I should expect that this line would go perfectly horizontal line if I add more time. So I'm gonna make it 800 instead of 520, and I'm running the file now, and you would be confused and surprised to see that this is going down. So after 600 or something, the height is decreasing, and this doesn't make any sense, and it's not logical, and it's not right. to see something like this. And this is what I was talking about. This is the function is getting stiff at this values of the time. So there was no stiffness here in the function until you reach the 550, and at this point you'd see that the points are getting really close together, and kind of at some point they are almost overlapping, and the values of the height are getting lower, which is not physically right. And now we will see another case that I'm now calculating this using the ODE 45. I'm gonna calculate it. I'm gonna call it S for stiffness, and I'm gonna use ODE 23S. So I have now two outputs. I'm gonna make the legend as closed tank or ODE 45, and I'm gonna make another plot that will be ODE 23S, and I am going to just hold the plot and plot the TCSH and make it red and square, for instance. Okay, so I'm now, what I did, I just solved the problem twice, once with the ODE 405 and once with the ODE 23, and I'm gonna plot them together on the same graph. And I want you just to notice a couple of things. The first is that it's easy to notice here that the height for the ODE 23 is constant, even after 800. So you'd see they are kind of going together until it reaches the 600 and something, 600 like 50 or 40, and then the difference started to appear. There is a difference in the height here because of the ODE 23 is dealing with a stiff functions. It can deal these kind of functions while the ODE 45 cannot, and it's giving some errors. The second here is that you would see that the distance between the points in the ODE 45 function is constant. It's giving you a constant increment between every 2 points until it reaches this point, of course, and then started to give the weird results. However, for the stiff function, it's giving not equal increments. It's going from here to here, and then you have 2 points in between, then 3 points in between, and then you like 3 points in between. So it's not going with a constant distance, and this is how it deals with the function. It's not it calculates the increment based on the stiffness of the function, and that's why it gives more accurate results in case of stiff functions than the ODE 45. So again, this is a case where we have a function was not stiff, but at some point with the inputs, it became a stiff function, and we had to deal with it as a stiff function. So I hope this helps, and I hope you'll be able to figure out the right function that you would use for your problem. And again, the documentation is full of information for anybody who is interested, and it will be more than enough to give you the information that you need to pick the right function. So I hope it helps, and I'll see you in the next video, inshallah. Goodbye.